Hi everyone. This is just a quick video to finish up the notes on what a titration is. So we talked about the setup of all of the equipment, right? So you can review those in the notes. I'm not going to go through them now. So let's talk about the work with it. Now, a titration again is an analytical method, so you're going to use it to analyze a substance, which will be your titrant. It's what your unknown is. You don't know the concentration of it, and you'll do an acid base titration to see what the pH is, work backwards, or a redox titration, again to determine concentration, just using different materials, or a precipitation titration. All right. So when we're talking about an acid base titration, we're going to use an indicator to tell us when the equivalence point is reached. So the equivalence point is when your moles of acid equals your moles of base equals your moles of salt formed. Now, the indicator actually changes color just before the equivalence point, or right at it. Once our indicator changes and there's no more ambiguity to it, there's no difference to it, that is the end point. This is just a chart of common pH indicators. We'll talk about this in more detail in Unit 8, but let's say we had a reaction where the equivalence point is around, I don't know, we'll call it the Q point, is around a pH of, let's say, 5. Which indicator would we use? So what we'd do is we'd look at pH 5, and change colors there. So we'd look at pH 5 and look for an indicator, we'll pretend it's a straight line, that has a change at or just around that. So that leaves out thymol blue because it's orange before and after that. Methyl orange is a maybe because of this transition here. Brothymol blue is a maybe as well because its color changes very close to our endpoint. But Congo red would be our best choice because we have, or possibly our best choice, because we have a color change close to that pH, but it's pink, light pink to dark red. That might be a little hard to tell. Same for brome crescel green, and we'd leave out methyl red because there's no real color change there. Same thing with brothymol blue and phenol red. Out of these choices, brothymol blue would actually be the better choice, I think, because it changed just before. All right, so if we go from that light green to dark green, we know that it's done. If we were in class doing this, we'd be doing a strong acid, strong base, which has an equivalent of 7, and we'd be using phenolphthalein because there's a transition from colorless to pink. And we'd be shooting for that light pink to be just on the north side of done. All right, here's a picture of what we'd see if we were titrating with a base using phenolphthalein. We get a light pink color when we're at our endpoint, dark pink color if we've gone too far. Now, this is a reminder of what pH is and how to calculate it. We'll talk about that H3O plus in Unit 8. What we need to remember is this point here. at the equivalence point, moles of acid equals the number of moles of base. So it makes our stoich real easy to do. Now, this is some quick math for it once we know that that relationship is true. Moles of acid equals moles of base. We can use this MAVA equals MBVB formula. This gets us our molarity of acid times the volume, gets us the moles of acid. Same thing on the other side for the base. It looks like the dilution formula, but it's not a dilution. This is not an M1V1 equals M2V2. Now, as we'll see in Unit 8, if we're working with a diprotic acid or diprotic base, we just multiply the side that makes two, either hydroxides or H pluses, by 2. That will get us there. All right, but right now we're just working with strong monoprotic. So let's look at this problem. A student titrates 20 ml sample of a solution of HBr, so that is VA, with an unknown molarity. So we don't know MA. The titration requires 20.05 milliliters of 0.1819 molar sodium hydroxide. There's our MB. What's the molarity of this solution, of the HBr solution? All right, so we need to know how many moles of acid we had, and we can use our MA VA equals MB VB. So let's plug those values in, or substitute, sorry, we don't know MA. Our volumes, as long as they are the same unit, can match. Then we can just plug those in. $9 times 20.05 mils. All right, so if we just divide both sides by 20, we'll get to our answer. All right, so let's plug that in. So what we're going to do is 20.05 times 0.1819 divided by 20.00, and we get to the right number of sig figs, 0.1824 molar. Is the concentration of the acid. So it's a pretty straightforward stoich problem. Let's look at the next one. All right, I'm not going to read this entire chunk of text to you. Take a moment to pause and read it. Now, you might be overwhelmed with this. This is pulled from an old AP exam. They will throw walls of text at you to try and distract you from the problem, make you feel like you don't know what's going on, but we can figure this out. So what we're going to do is pull everything that we need to know. So let's start by identifying our unknown here. What do we need to do? All right, we need the concentration of sodium hydroxide. So we're looking for the molarity of the base. Oh, we're given a mass of an acid. Tells us right here there's one acidic proton. I have a mass and a molar mass, so we'll need to convert that. And we've got a volume of sodium hydroxide. So there's our VB. Well, if I'm looking for molarity, I need volume and moles. All right, there's the info we need. So let's solve it. So let's write out our work. The first thing we need to do is go from grams to moles for our acid. All right, so remember, if we're going from grams to moles, KHP is the abbreviation for this big compound. But grams to moles, we divide by the molar mass. So let's see, we've got 1.3009 over 204.22. So that gives us 0.00637. Actually get 4 sig figs 0 moles of our KHP. So it tells us that it is monoprotic. Sodium hydroxide only grabs one proton at a time. So we're going to have some easy math to do there. All right, it's a 1-to-1 ratio. KHP is gone, getting us 0.00637, forgot a 0, moles of sodium hydroxide. And then to get concentration, I need to divide this by our volume in liters. So if I move my decimal 1, 2, 3, it's 0.0412 milliliters. Sorry, liters. All right, and let's do that. So this divided by 0.04120, 0.1546 molar sodium hydroxide. All right, and then we'll do some more more titration practices in next class.